Hi everyone. I wanted to take another look at the algebra of functions and an area that kind of presents trouble for students. In particular, let's look at some examples that deal with the division of functions and then determining the domain of that quotient. Let's look at a few examples. So let's look at this example. We're going to let f of x equal x plus 2, and we'll let g of x equal the square root of x minus 1. If we want to find the domain of f divided by g of x, let's first find what this function or the quotient of this division would look like. We would have x plus 2 divided by the square root of x minus 1, and this is the quotient. This is our new function. But if we want to find its domain, we have to pay attention to the denominator because we have a rational function, so we want to look at the denominator. And we know that the special cases that alert us when we're concerned with domain and range are when we have a radical and what happens underneath the radical, the radicand, what it equals, and also when we have a fraction. All right? We know that can't take the square root of a negative number and still get a real number as the result. And we also know that dividing by 0 is an undefined operation. So in this particular case, we have a radical that is in the denominator. Well, we never want our denominator to equal 0. And also, we don't want what's underneath the square root to be negative because then we would have an imaginary result. So we want to put some restrictions on the domain in order to keep this function defined. So we're going to say that we want what's underneath the radical sign, which is x minus 1. We want it to be positive, which means it needs to be bigger than 0, and we never want it to equal 0. So if we solve this inequality, we would add 1 to both sides, and we find that our domain is where x is bigger than 1. Now we want to write this in interval notation. It might help if you draw a graph. If we draw the graph of this inequality like we discussed in class on Monday, if we draw the graph, we have 0 and 1. We're not including 1. So we have an open circle. Let me change the color. And we're using the inequality as an arrowhead to tell us the direction that we're going. So this, written in interval notation, would look like 1 to positive infinity. And that's the domain of f divided by g of x. Now let's take a look at the domain of g divided by f. So again, we had f of x equals x plus 2, and g of x equals the square root of x minus 1. And we want to find the domain of g divided by f of x. The quotient of g and f would equal the square root of x minus 1 divided by x plus 2. Again, we have two special scenarios that we have to consider here because we have a radical and we have a fraction or a rational equation. So let's look and see what happens here. First, let's talk about the denominator. It really doesn't matter which order you consider it, but we will consider the denominator first. Our denominator of x plus 2, we know dividing by 0 is undefined, so we never want what's in the denominator to be 0. So we take the x plus 2 and say it can't equal 0. Solve for x algebraically by subtracting 2 from both sides, and we find that x cannot equal -2. So x can be any number except -2. However, we have to take into consideration the restrictions that are imposed by having that radical in the numerator. So let's look at the numerator. The numerator was, or is, the square root of x minus 1. We can't take the square root of a negative because we are only talking about real numbers currently in the course. So we need what is underneath the radical sign to be positive. And in this case, in all cases, positive numbers are greater than 0, but in this case in particular, this radical is in the numerator. So our numerator can be 0. 0 divided by a number is 0. So we can have the equal to bar in this inequality when we're trying to find out the domain. Solve this algebraically by adding 1 to both sides. And we find that x needs to be greater than or equal to a positive 1. So now we have to take both of these into consideration, the fact that x can't be -2, but also we have to consider that x has to be bigger than or equal to 1. Let me clear this board and then we'll finish talking about this. So we want x to not be -2, and we want x to be greater than or equal to 1. I'm going to graph both of these on the same number line, and then we'll have our discussion. So -2, -1, 0, 1, 2. Just making up a number line, putting arbitrary numbers on it. All right, so x can be anything other than -2, which means my x can look like anywhere over here. Let me change the color. And all the way over here. Okay? And that's what the graph will look like of x is not equal to -2. That's what we've graphed in the green. All right, now let's see what it looks like when x is greater than or equal to 1. X is greater than or equal to 1 means I'm including 1, and I want x to be bigger than, using that as the arrowhead, it needs to be this way. My solutions will be where the green and the red overlap, okay? They overlap here. So the domain of g divided by f is 1 to positive infinity. The reason nothing in the green is in the domain is because nothing in the green will satisfy the condition that x needs to be greater than or equal to 1. However, everything that's in the red will satisfy the condition that x needs to be bigger than or equal to 1 and that x does not equal -2. That's why our final answer for the domain for this only takes into consideration this portion of the graph, because that is where the green and red would overlap.